Hello, my name is Juan Romero, and this is me trying my best to explain what backpropagation is. So backpropagation, essentially what this is, it's a method for calculating the gradient of the cost function with respect to the weights and biases of a neural network. So this is what makes a model learn from its mistakes. So our cost function, like I explained in the previous video, is essentially just telling us how far off our prediction was. So with backpropagation, we can adjust the weights and biases so the network makes better predictions in future attempts. So the gradient. Okay, so essentially what we're trying to find is gradient descent. What is the input vector that we can put into our function that if you take a look at this image here, let's say we start where this ball is at, right? What is the input that we can take so that we find the minimum of this slope? And why we want to find the minimum is because we want to minimize the cost of the function. One more time, what the cost function essentially is we're taking our actual inputs, we're subtracting it by the expected inputs, where we are going to square each of these differences, and then we're going to add up all of these squared differences, and then that's going to give us some number. This number is going to be the cost. So now this is going to be the cost, and this is telling us if we get a really high number, we're going to say that our model at this one is not really giving us what we want. Okay, so now how backpropagation actually works. So let's say that we ran our model for the first time. Now I just drew this number 3 as let's say we're inputting this into our model. So now, since this is running for our first time, it's important to note that this could have been run with random weights and biases, right? And so we're not really expecting the outcome to be what we want. Now, let's say that we ran this through the model, and so it gave us these output values, and we can assume that this 0.2 is representing that this model predicts that it's a 1, this 0.8 predicts that it's a 2, and so on. So it's a 3, it's a 4, and it's a 5. But what we expected here, right? We can tell that this is a 3, but obviously we're changing the model to. What we're expecting here is that this node representing that the model predicts that it's a 3 is a 1, and all of these others are 0, or at least very, very close to 0. This tells us that the model is pretty confident that this number here is a 3. Now, again, these are numbers just that I made up, but now in this particular case, let's say that we ran the model and it returned the highest value here is actually 0.8, but this is the node this is a node saying that the model thinks it's a 2. Not only that, but these numbers here it's not really super confident that it's a 2. As you can see here in this node that tells us that it thinks it's a 5, it's actually really close. So it said it's a 2, but it's not 100% sure like how we want it to be. Okay, so the goal is to increase the activation of desired output node and decrease all the rest. That's here the ultimate goal. But we can't directly change the output values. We only have the influence on the weights and the biases. So when we and I'm gonna say this in the next slide, but when we change these weights or the actual now when we change these weights, we want to either increase or decrease them proportional to the activation value. Okay? So for example, if we have a 0.8 here, this model is telling us that, although not 100% sure, right, but it's telling us that it's sure that this is a number 2. So it's important to remember that this value here, 0.5, and by the way, it's the same 0.5 as this one, as the output node, is just a result of this formula here. So essentially what this is saying is that it's the sum of each of these weights multiplied by their respective activation values. So 0.8 would be the activation value, and then it would have a weight associated to this. And then at the very end, we add a bias that we determined. This is just a constant. It's just a number that we determined beforehand. And then we pass this number here, whatever this number is. It could be a really big number, really small number. And we pass this number onto the sigmoid function. And essentially what the sigmoid function is, it's just going to return us a number between 0 and 1, right? Which is why we have these numbers here between 0 and 1. Okay, so we have options to bump a value to the desired value that we want. In this particular case, we have 0.5, but we want to actually increase this so that it's a 1.0, right? Like I said, we expect this to be a 1, but we got a 0.5. Okay, so what happens here? 0.5. In this particular case, when we pass the number 3, these neurons here fired. Okay, but we got a 0.5, but we want this number to be a 1. So let's say that in this case, the weight here for this activation value was 1. Okay, let's just do nice, simple, small numbers. And let's say that the weight for 0.1 was also 1. Now what happens here is that we have to realize that if I change this number here to 2, as we can see here, the activation and the weight will be multiplied. The product of these two will be now 1.6. So now we will have changed this from 0.8 to 1.6. Now if we change this weight here from 1 to 2, sure, we doubled it like we did here, but this one's only going to be 0.2. So we can realize here that in order to increase this one, in order to increase 0.5 to 1, we actually have to increase the weights of the neurons that already have a high value in them. Okay, because changing these offer me a better increase than changing, for example, 0, right? If this is a 0, and no matter what I multiply it with, it's still going to be 0, right? And then this one I'm going to have to multiply it a pretty good amount to a pretty big number to get close to what I can multiply 0.8 by, let's say, 3 to give me a higher increase. Okay, so this way, the neurons that get most activated when the model thinks it's a 3, or at least sees that it's a 3, get adjusted so they fire when it's actually a 3. Okay, so this example is only what this output node wants. What this output node here wants to increase to a 1.0. But we also need to perform this process for every other output node as well. So 0.5 wants to increase, 0.8 wants to decrease, or we want it to decrease, and 0.2 we also want it to decrease, 0.4. But at the same time, it's also about how much does it want to increase, how much does it want to decrease. 0.8 wants to decrease a lot, 0.5 wants to increase double the amount, 0.7 wants to also decrease a lot. So this is where the idea of propagating backwards comes in. So in the right, So in the right, in this example, a 2 was inputted. And we can see just by this picture that it got it all wrong, right? So this node here was predicting a 0, this is predicting a 1, this one's predicting a 2, but it only got an activation value of 0.2. And it actually thinks that it's a 3, but it also thinks that it's a 6, right? Equally, right? It's fully lit up for 3 and it's fully lit up for 6, and it's almost fully lit up for 2, for 1, sorry. That's not what we want. So in this case, the output node that represents a 2 wants to have a higher value. So it has its thoughts about what the activation value needs to look like for each of the previous nodes in the previous layer, right? Now every other node needs to have a smaller value. And so they also need to say how the previous node's value needs to be adjusted. What does this mean? This means that for this particular input, when we have inputted a 2, right, and we got this these output values, right, we want 2 to increase. So this particular node here, 0.2, is going to go through this process that I explained. Kind of have a list of what it wants these values to look like, whether it wants these to increase or decrease, but also 0 has to decrease here, 1 has to decrease, 3 has to decrease, and all of these other ones except for 2 actually has to increase. So 0 wants to decrease, but just a little bit, right? But we're still going to apply this that I explained to 0, and 0 is going to have its thoughts and say, well, in order for me to decrease, I need this layer to look like this. Let's say this second row was what 0 needs to look like, right? What 0 wants this layer to look like. 3 wants to decrease a lot, so again, we're going to apply what I explained. And 3 is going to say, well, I need this layer to adjust by this amount, and so on and so forth. Now, we're going to add up all of what these neurons are telling this layer to change by. And so now we have this here, and these arrows are essentially the summation of all of these changes. Now, this layer here is this layer. This layer needs to change. This one needs to go up. This one needs to go down. This layer, every single node here is now going to recursively do essentially this, and then tell this layer, this node is going to say, well, I need this layer to look, I don't know, I need this one to go up, I need this one to go down, I need this one to go up for me to go down. This node is going to say, I need this one to do something, this one to do something else for me to go up. And that's essentially what backwards propagating is. All right, now that we have done that just for this one input, in this case, for the input 2, we actually have to do this for now every input. Okay, and now once we figured out more or less how we need to change every input so that it detects a 2, so that it detects a 5, a 0, a 4, we're gonna now average all of these. So this first row is the changes we need to make to the very first weight, and at the second one to the third one, and so on. And once we get these values, this now is our gradient. This is a vector that we are going to input into our overall function so that we can get closer to that minimum. And essentially, this is how backwards propagation works.